Chapter 5, Section 4, Composition and Inverse of Linear Transformations. In this section, you will learn composition of linear transformation, where we combine multiple transformations sequentially. You will also learn how to inverse the transformation, that is, how to restore the original vector space. In addition, you will see a case of non-invertible transformation, where we cannot restore the original state. In the previous section, we have explored what matrix representation means in linear transformations. It is the process of expressing a linear transformation as a matrix and using that matrix to transform vectors. Here, a matrix works as a tool or operation that represent a linear transformation. By using matrices, we can perform various geometric transformations such as rotation, scaling, reflection, and shear within a vector space. When linear transformations are applied sequentially, they form a new transformation. This is called composition. The composed linear transformation can be expressed as a product of matrices, meaning that multiple transformations can be applied through a single calculation. For example, if the matrix A1 is applied first, and then the matrix A2 is applied, the composition of the transformation is written as A2 after A1 on V. Since matrix multiplication is not commutative, the sequence of transformation is important. That is, order matters. Matrices are generally multiplied from the left side of the vector they act upon. If A1 is applied first and A2 second, the composition is expressed as A2 after A1. Let's see an example. We have two matrices that perform a linear transformation. Our theta is a rotation matrix that rotates the space by theta degrees. Sk is a scaling matrix that scales the space by a factor of k. The composite transformation that first rotates and then scales is represented as the product of these matrices. This composite transformation represents a rotation by theta degrees, followed by a scaling by a factor of k. Next, let's apply a linear transformation to a vector v with real numbers, using matrices with real numbers. The rotation matrix rotates the space by 90 degrees. The scaling matrix scales the space by a factor of 2. The composition rotates the space by 90 degrees, then scales it by a factor of 2. If we apply this composition, the vector v will be transformed in this way. Let's confirm that this operation is a composition that rotates, then scales. First, rotate the vector v by 90 degrees. Then, scale the resulting vector by 2. We can see that the resulting vector is equivalent to the vector that we obtain by applying composition. Composition has some properties. Here, we should note associativity and non-commutativity. The first is associativity. When composing 3 or more transformations, the order of multiplication does not change the result. The second is non-commutativity. In general, the order of matrix multiplication matters, meaning The result may differ depending on the order of transformations. Rotating and then scaling leads to a different results from scaling and then rotating. A linear transformation may have an inverse transformation that restores the vector space to its original state. For a transformation T, its inverse is denoted as T to the power of minus 1. We can recover the original vector using the inverse matrix. For matrix A, the inverse matrix is denoted as A to the power of minus 1. When a matrix A is multiplied by A inverse, the result is the identity matrix I. The identity matrix represents a transformation that does nothing. That is, it leaves vectors unchanged. As an example, let's apply matrix A to a vector V. To undo this transformation, apply A inverse to the result. As we can see that applying the inverse matrix restores the vector to its original state. Let's see a more concrete example. Consider this matrix A. This matrix represents a scaling transformation. It scales the x component of any vector by 2 and the y component by 3. When we apply the matrix A to the vector V, the vector is transformed in this way. The inverse matrix of A will undo the effect of the scaling transformation by dividing the x component by 2 and the y component by 3. Let's apply A inverse to the transformed vector. The result is the original vector V. The inverse matrix reverses the effect of the original transformation. Let me explain the conditions that determine whether a linear transformation has an inverse. Not all transformations can be undone. If the inverse matrix does not exist, we cannot reverse the transformation, and thus we cannot restore the original state by multiplying with the inverse matrix. For a matrix to have an inverse matrix, the matrix must have a non-zero determinant. For a 2 by 2 matrix A, the determinant is given by this formula. If the determinant is 0, the matrix does not have an inverse. The matrix whose determinant is 0 is called a singular matrix. In a singular matrix, the column vectors are linearly dependent. A singular matrix collapses or distorts the space, making the original information unrecoverable. Now, we have a mathematical understanding that if a linear transformation is represented as a matrix that does not have an inverse matrix, we cannot restore the original state of the transformed vector space by multiplying a matrix. In what cases can't we undo a linear transformation? If the transformation results in a loss of information, it is impossible to recover the original state using an inverse matrix. In such cases, the matrix is singular and has no inverse. These transformations are called non-invertible transformations. A typical case is projection. A projection transformation reduces the dimension of a vector space by flattening it onto a lower dimensional space. Think of projecting a point in 3D space onto the floor. The information along the z-axis is lost in the process. Once the point is on the plane, we can no longer determine its original position along the z-axis. Let's take the following example of a projection onto the x-axis in 2D space. This is the projection matrix P. If we apply this projection matrix to a vector, we get a new vector. Here, the y component is lost, and only the x component remains. As a result, it is impossible to recover the original value of y from this projection. Therefore, no inverse matrix exists to reverse this transformation. The reason we cannot reverse some transformations is that information is lost in the process. For example, projecting from 3D to 2D eliminates one dimension's worth of information. Multiple vectors map to the same result. When different vectors are transformed to the same vector, it becomes impossible to identify the original vector. In such cases, the transformation has no inverse, and we cannot recover the original vector or state using an inverse matrix. Let's summarize the key points. The composition of linear transformations enables us to combine multiple transformations into a single transformation, expressed as a product of matrices. Inverse transformations restore a transformed space to its original state, and we can inverse transformations using inverse matrices. However, a linear transformation is non-invertible when the transformation loses information that is necessary to restore the original state. Thank you for watching.